Exponential functions part 2. First, I just want to go over the different kinds of bases that you could have. So this is 1.6. In the previous video we had a base of 2 and we saw how that shot up. 1.6 seems to shoot up also. This one's 1.2. It does shoot up, but it's on the same axis, the same window. It shoots up but slower because the 1.2 is not as big of a base as 1.6. Then when it goes all the way down to 1, the x is just 1, so you just have 30. So it's just a straight line across there. What happens when you go below 1 at 0.9? Then it seems to be decaying, because every time you have another x value, you're hitting another 0.9 of what you had, so you're going down 10% each time. In other words, each new value is 90% of what it was, or 0.9 of what it was, so naturally it should go down. 0.2 is real small, so it goes down real fast, like that. So here are the rules about that. Here's your exponential equation form. And if b is greater than 1, the graph increases exponentially. That's like one of these. Exponential growth. If b is less than 1, the graph decreases exponentially. That's one of these. Goes down. Exponential decay. And the b equal 1 case, we don't, nothing comes from that. Well, that doesn't come up in practice. Okay, so part 1 showed exponential growth. That was part 1. Here's an example of exponential decay. Alright, so in 1975, a nuclear test left 2,000 millirems of radiation at the test site. Suppose the radioactivity is decaying at 2% each year. That is, each year the amount of radiation is 98% of what it was the previous year. Find the exponential function r of t that models the amount of radiation present t years after 1975. So 1975 is year 0. Graph the function. If the area is safe to return when the radiation reaches 440 millirems, in what year, the actual date, will that be? You know, we all receive a certain amount of millirems per day from the sun, from microwaves, from all kinds of things that we're around every day. So there is a minimum amount where it is safe. Okay, so here's our equation. Starts out with 2,000 at year 0. If you put a 0 up for t, 0.98 to the 0 is 1. 2,000 times 1 is 2,000. So it starts with 2,000, year 0. And it decays 2% each year. So in other words, every year it's 0.98 of what it was the previous year. So that's why the base there is 0.98. Alright, so we're going to figure out this problem. So we put the function in, y1, we put the 440 in. We're going to find out where this function becomes 440. Now I showed the window here. I had to fool around with this window to get the intersection to show up, and when you do this window, it shows up right here, the intersect. Then you do a second calc intersect. Second calc intersect that we've done plenty of times before. It finds that intersection point, which is at this value, 74.9. So that is approximately 75 years, and 75 years after 1975. So the area will be safe in that it goes from it ends up being 440 millirems. 75 years after 1975, which is in the year 2050. We'll have another way to solve that kind of equation later when we study logarithms. So we wouldn't have to necessarily do a second calc intersect to solve the problem.